So, in the earlier class we have seen that we can have three types of processors, right. Typically one is a general purpose processor, or those are application specific instruction processors and application specific ICs, which are purely or we can call it also as single purpose processors. That means they can, now there is a slight difference between an ASIC and a single purpose processor. Whenever we use the term processor, then there is some programmability that is being mentioned along with it, right. But in the case of ASIC, it is an application specific IC that has been designed for a specific purpose. So, this is completely hardwired, right. This is completely hardwired and I do not have any scope of programming it and changing the functionality, but for single purpose processors there may be a little bit programmability. Now, yesterday or in the last class we also had talked about the instruction set architecture. The instruction set architecture is what distinguishes between the architectures of the different processors, right. Say Pentium will have a set of instructions, and those instructions, those instructions will have different features, and accordingly there will be different instruction cycles, different ways in which the instructions are executed. Now, for ARM, if we move to ARM, another processor or some other DSP processor, in that case also we will have different instruction sets. Now, a general purpose processor, since it caters to a larger scope of different problems, the instruction set is quite large. On the other hand, for ASIPs, application specific instruction processors, these are much less. Now, the best example of a general purpose processor, one maybe you can say Spark. For Spark machines we have got different processors, for Pentium machines we have different processors, but for embedded system the general purpose processor is represented by the microprocessor. Okay. A microprocessor, all of you are exposed to this. There are different varieties of microprocessor, different companies are coming up with microprocessors. Now, these microprocessors are also general purpose processors. They have got their control unit, they have got their arithmetic logic unit, they have got a relatively larger instruction set, there are ports. So, typically a microprocessor, what will it have? A microprocessor a hypothetical microprocessor will have, of course, some control. It will have an arithmetic logic unit. I am assuming a simple microprocessor where we have got only one ALU, no parallel processing. There is a bunch of registers here, which are also known as scratch pad registers. And there are some control registers. Some control registers like the program counter, instruction register, all those things are there which are required for the control. All right. And there are some status flags. Okay, some status registers. These are the status registers. Besides these, there may be in the modern microprocessors, there may be some on chip memory, okay, some on chip cache, there may be some on chip memory. On chip memory, right. And there are, so if I now encapsulate the microprocessor, then there are some interfaces for communicating with the external world, like there can be interrupt lines, there can be other lines for memory interfaces going to the external memory, all right, and there can be ports for communicating with the external world, all right. Now, these ports are often programmable, right. So, these are often programmable ports. That means that I can program these ports either to be acting as an input or as an output. So, this is a microprocessor. Now, this is driven by a clock, all right, of certain megahertz, some megahertz. Now, it is going up further to thousands of megahertz, but gigahertz is now a commonplace now. So, we are having, but by the way, just the increase in the clock speed is coming to a saturation now. We have seen in the past decade that the clock speed of the microprocessors were shooting up, right, but now that is gradually saturating because of technology reasons. Now, so this is, so we have got some components inside the microprocessor which executes different instruction set. Now, where does we say the instruction set architecture? Now, what role does this instruction set architecture play with respect to this architecture? The instruction set architecture is modeled by the way the instructions taken from the memory, all right, and through some path, data path, it will come to the instruction register, right, and that will be decoded in the controller. After the decoding, different parts data can be brought in, fetched, or I can fetch data from the registers. This can be connected with the registers or with the other lines. Now, all these, for the different instructions, there should be different paths that will be activated during execution, and that activation is being done by the controller, right. So, the controller, as we discussed, the controller is essentially a state machine which is in the present state. Depending on some inputs, it goes to the next state, like that it goes on, right. And the data that was coming, suppose I fetch the instruction from the memory. So, there must be a data path that will bring it here. Say in one instruction, I want to fetch the data from the register, two registers, this one and this one, say here, and the other one from this register here, and do the ALU activity, and the result will go here. That is one scenario. Now, in the another scenario, maybe the instruction that is being executed is taking a data from the memory and is coming here. Another one is coming from this register here. Now, how can that be made possible? Now, I have got only one ALU. I have got one ALU and there are two inputs. Now, the data can come from this path or from another path or from another path. So, how do I select which path should be activated depending on the instruction? That is, all of you will immediately understand, we need a multiplexer here, right. That is why, if you recall in the earlier class, we said that a data path consists of the computing elements, the WATs, the multiplexers, buffers and all these. Okay, that is the data path. So, this is how a microprocessor, which is the most we can consider the general purpose processor, is working. Now, for an embedded system, how do we go about selecting a microprocessor? Now, how do we select a microprocessor? That is a very important issue when we go ahead with some embedded system design. Now, one thing is of course speed. How much speed? Another point is the power that is spent, the size, cost. These are all the technical specs maybe. Okay. The other aspect that you should also look at is whether you have got some expertise, whether I am familiar with the instruction set, okay. Your familiarity, the designer's familiarity, expertise and all those things. Okay. So, that is also an important point, because as we said that the time to market is a very important thing. It is better if you can choose a microprocessor about which you are familiar, you have already done some developments. So, better that can also come into your optimization decisions. Okay. Now, when we I would like to touch upon how do we measure, how do we talk about speed? When we talk about speed, what are the factors that come with speed? One is of course the clock speed. Okay. The faster the clock, the faster this clock is, the faster the instructions will be executed, right. That is true, but instructions per cycle may differ, right. Different instructions may take different cycles. Therefore, clock speed will determine the, say this is the clock pulse, right, and we have got say here some fetch is being done, some decode is being done, I am doing the fetch operand and then I am doing the execute, then maybe I am doing some write back here. Now, for some instruction I may need all these. For some instruction maybe just I will not need any operand, there is an immediate data. So, I can execute that. So, the instructions cycle is very important. Another point is the number of instructions I execute per second. Now, the clock speed is there, but also the instruction cycles are important, right. Now, therefore, we have got different benchmarks to see how the microprocessors perform. For example, just for the reference, Drystone benchmark is a very popular synthetic benchmark that was developed in 1984. Okay. It talks about the MIPS, million instructions per second, and now MIPS architecture is also another architecture in the paradigm of RISC machines, right. There is besides Drystone, there is spec, okay, is a set of more realistic benchmarks, but this more tuned towards the desktops and that sort of thing, spec benchmarks. There are other benchmarks also, you can find that out. So, often when we look at the microprocessor that we will be using, we look at the different parameters. Now, power, time and again I will be emphasizing on the power that it consumes. Okay. If you increase the speed, as it becomes faster, then the power consumption also is high. The arrangement that you will have to make for the heat dissipation will also be much more complicated. Now, given this, let us have a look at different general purpose processors. If you look here, we can see that Intel's Pentium 3, the clock speed was 1 gigahertz, IBM PowerPC 550 megahertz, right, MIPS machines 250 megahertz. I should have mentioned while I was discussing about microprocessor about the strong ARM processor. This is a very important processor that has found a lot of application, ARM and also strong ARM. Okay. Now let us just restrict ourselves to microprocessors for the time being. I will come to microcontrollers and DSPs later. So, you can see that they have got certain bus width, that means how many bits of data it can handle at a time, 32 or 64, it can be in two forms. The speed, number of the MIPS, how many million instructions that it can execute per second, around 900, 1300. Similarly, power, you can see Intel Pentium 3 consumes 97 watt, whereas IBM PowerPC is 5 watt. Now, how many transistors are there? Those things are there. The price is more or less same. Okay. So, we can here is just a snapshot of the different general purpose processors. Next, let us come to ASIPs. The most common ASIPs means application specific instruction processors, and the most common ASIP is a microcontroller. Now, a microcontroller can be considered as an ASIP. What is there in the microcontroller? A microcontroller has got a microprocessor, no doubt, in it, but microcontroller is essentially used for embedded applications. Okay. It has got some ways and means. So, what we do, it has got the facilities for reading sensor data, some actuation, we will be able to actuate data. It deals with mostly events. As the events take place outside, as it is a reactive system, data is present, but not in a huge amount. We have got microcontrollers in applications. One of the applications, VCR, is already becoming obsolete. A news item came out that the last VCR has been produced. So, but once VCRs were very important applications, video recorders and players. But now, say for example, in disk drives, in digital camera, even in microwave ovens, washing machine, all those things have got microcontrollers. Now, how does the microcontroller differentiate itself with a microcontroller, microprocessor? A microcontroller will have, along with, we have seen the diagram of a microprocessor here, but in addition to that, for example, the instruction set of a microcontroller will be much less. So, the control circuitry will be simpler. The data path will also consequently become simpler, right, but it has got in addition some devices which are very important for embedded system development, like timers, A to D converters, communication ports, okay, and there is a register space, of course. It also has got some on chip memory, and there usually we have got there some program memory and data memory. As we will see in another variety of ASIPs, that sometimes we will deviate from the typical von Neumann architecture, and we can have program memory and data memory separately. Okay. And it allows you to have direct access to several internal pins. Okay. Many of the chips pins, the programmer can directly access them, and there is in the instruction set, although I said the instruction set is simpler, but there are some specialized instructions for bit manipulation and other low level computations. So, these are something which are not there in a typical microprocessor. We have to, if I select a microprocessor, then I have to select an AD converter, I will have to have a separate timer and all those things. Now, in this case these are all built in. Okay. So, a timer, all of you know, a timer can act as a timer or as a counter. So, what does a timer do? A timer is usually set with a preset time, and at each clock it counts down, and when it becomes 0 it gives a pulse. A counter, on the other hand, is reset to 0, and at every clock pulse it increases, counts up, and at any point of time I can find out what is the time elapsed. Now, one in the context of timer, one very interesting embedded application requires often watchdog timers. What are watchdog timers? Watchdog timers are as if a watchdog, a timer is watching out for an event to occur. Say for example, there is a machine and I want to monitor the health of this machine, okay, some machine M, and as a signature of its health, it will send a pulse maybe every 15 seconds, every 15 millisecond. Okay. A pulse comes at every 15 millisecond, and there is a watchdog. I have just deployed a small system which will set an alarm if there is a health hazard, which will set an alarm if there is a health hazard, otherwise it will not do anything. How will you implement that? There is a, so this is a small system within which I will have a timer. Have all of you got the problem? That I want to ensure that this is healthy, and the way of knowing whether it is healthy or not is every 15 millisecond I must get a pulse from here, right. So, what should this timer be programmed to? This can be, this should be programmed, and this timer should have 15 millisecond or say 16 millisecond, whatever you program, and this pulse will reset or set the timer again to 15 millisecond. Suppose it starts with 15 millisecond, right, and it is counting down 14, 13, 12 like that. If it comes to 0 and this pulse does not arrive, then the alarm will be set. Otherwise, if this is healthy, then this will come and it will again rejuvenate this. A very simple application. All of us, we have got a pulse rate, right, and so we can also monitor that in that way, but it is a question of, so it is a watchdog timer. These are different, a very important application of timers in embedded system, where we watch out for an event to occur. We are expecting some event to occur, right, and whether that event is occurring or not. All right. So, timers, AD converters, communication ports, all these things are involved in a microcontroller. The other very important ASIP is a digital signal processor. Or DSPs. Okay. Now, a DSP is used for, as the name implies, it is used for signal processing. See, often we need very fast processing. We have got streaming data, data is coming continually, and we have got a signal processor which will have to process the data on the fly. All right. For example, it can be a cell phone's voice filter of a cell phone, or a digital TV. Data is coming, I have to process that and display that. Music synthesizers, other things. So, consequently, a DSP needs fast execution. So, unlike a typical standard microcontroller, which has got one processor, one ALU and all those things, here in a DSP we often have multiple, different execution unit. I would say several execution units. Okay. One very important instruction that is there in its instruction set is multiply accumulate instruction. Now, one common operation in any DSP is, a very common operation is, among other things, you will have something where you will compute something like this, some data maybe x I and maybe some other thing a I. So, there is a multiplication here. all right, and we will go on doing this. So, multiply and accumulate, multiply and add, multiply and add, all right. It is not, this is a multiplication, okay. X I multiplied by A I, and that is being added continually. Now, this type of operation is present in different DSP applications, like say discrete Fourier transform, fast Fourier transform. This is a very standard signal processing applications. All of these have got operations of this form. All right, or AJ, it could be 2, it could be 2 summations, etc. Now, therefore, in a typical microprocessor, how would we implement this? We require a multiplication, and that multiplication may require, if I do it without any fast multiplier, this multiplication will require more number of cycles, then I add it, again I multiply, add it, multiply, store, add, multiply, store, add, or I will have to have very fast multiplier, which is multiplying and then adding, thereby I am saving some time. But in a DSP, there are multiply accumulate instructions which are single cycle, single instruction cycle, specially designed, okay. And there are other instructions also besides the single cycle, this thing. There are scopes of efficient vector operations. Like for example, efficient vector operations. For example, it is often the case that there are 2 arrays, one is say x, another is y, and a lot of operations can be say x I plus y j, and we repeat it for say from I to from 1 to n or something like that. So, this addition, so there will be special instructions where this can be added in a much faster manner, parallel addition and those. So, those sort of operations will see the instruction set of some typical DSP processors. So, I would suggest that all of you try to look at some Texas Instrument TMS series DSP processors, okay, and look at their instruction set. For microcontrollers, you can see the typical say for microcontrollers, you can start with simple one. I would suggest that all of you look at 8051 is a microcontroller, which is Intel's microcontroller. Look at ARM and strong ARM microcontroller, and study their instruction set and compare it with a microprocessor. You can take any microprocessor. If you take the simplest possible microprocessor 8085, which all of you must have done, you can see that, and along with that you compare the instruction set of 8051, what is added there, what are the extra instructions, what are not there. Try to make a list. For ARM, you will find there are 2 different modes in which ARM processor can work. One is a thumbnail mode, and there is a normal mode. So, it has got a special thumb mode, okay, where you have got, you can work it in 32 bits and you can make it much less power consuming. So, look at, study these and also for DSP you study some microprocessors of Texas Instruments, and you will see how the instruction sets vary. Okay. So, that is an example of an ASIP. Now, the trend is for more and more even more customized ASIPs. We are trying for even more customized ASIPs. Earlier we had microprocessors as chips, right. Now, today we increasingly we are actually getting now what we call, earlier microprocessor was a chip, right, and we used to buy microprocessor. A chip. Now, we are buying intellectual properties or IPs. What is meant by this? We know intellectual properties means you invent something and you apply for patent, that is intellectual property. Here, although the name is same, it means you are getting some pre-designed cores. For example, these are nothing but some synthesizable, I will just explain it, VHDL, say VHDL, say. For example, I have designed a processor or a part of the processor, and I have designed it, I have tested it. Now, that description I am offering to others as a synthesizable form of VHDL code. VHDL is VLSI hardware description language. So, once you have that program, you have got that program, it is synthesizable. So, you can directly put it in your tool, not using your intellect so much for the design, because it is already designed. You just put it in your design tool and you are getting that processor or a part of the processor, maybe a fast multiplier. All those things are coming up as, and those are the core based design, or that is why these are cores, pre-designed cores available as synthesizable VHDL. Now, this much is offered to you. Now, you can customize, you take this, you can say for example, customize the data path, you can customize the data path of this, you can add a couple of hardwares, or instructions. What do you mean by you can add a couple of instructions? What is meant by adding a couple of instructions in this context? You have got something, and that has got some controller, some data path with multiplexers and everything is there, all right. Some elements are there, and there is some multiplier, there are some adders. Now, you want to add one instruction, you find that for my job I need to add one instruction or two instructions, that will make it even faster. Now, had it come as a chip, you could not have broken that chip and work it further, but here you are getting a VHDL code. Therefore, you can add, just as a software program, it is a function as if. Now, you can add lines to the function, so that you can add to the data path which will be implementing your desired instruction and then synthesize it. Is it clear? That is how, that is a trend now of taking this IPs and further upgrading them for further design. Okay. So, this is the IP based design, and this is a trend by which we can very fast go towards single purpose processors. Next day we will be talking about single purpose processors in much more detail.